Welcome to today's lesson, Steam Basics. Click the Start button to begin. In this course, you will learn about steam and identify what steam is. Learn how the energy of steam is used and identify the many properties of steam. Please allow at least 30 minutes of your time to complete this course. Taking full advantage of the steam utility depends on a thorough understanding of its potential and properties. The more you know, the greater the benefit you'll enjoy. To say it another way, the more you know about steam and how to control and use it, the greater the return on the investment in a steam system. Our journey towards understanding steam begins. Click play to continue. Steam is an odorless, colorless gas that is created when water is heated to its boiling point and changes state or vaporizes from a liquid to a gas. When heat energy is removed from steam, it loses its ability to retain a gaseous state and condenses back into a liquid. The resulting liquid is called condensate. The process of condensation happens quickly. The temperature at which condensation takes place is known as the dew point. There are various forms of condensate that are sometimes incorrectly referred to as steam. These forms, however, lack the molecular makeup of a gas. Some examples of these are the mist you see rising above relatively warm water on a cool day is in fact water vapor condensing in the air. The droplets on your bathroom mirror are formed when water condenses out of the relatively warm air onto the cooler surface of the mirror. Click play to continue. Let's take a closer look at steam's practical uses. Click play to continue. We use steam in our everyday life in many different ways. From the plastic and vinyl components of our automobiles to the paints and stains we use on our homes to the preparation and presentation of the food we eat, we use steam to make our lives more comfortable and convenient. Fuel is consumed to heat the water that becomes steam. The gas has value. It contains valuable and useful heat that can be used in a variety of purposes. In fact, steam is used in the manufacturing of more than 80% of the products produced by industry. Steam has several physical properties that make it particularly suitable and economically advantageous for these industrial purposes. Click play to continue. Let's examine the steam loop. Click play to continue. Most industrial steam systems are closed systems. When water vaporizes to become steam in the boiler, the expansion pressurizes the system. Steam is forced out of the boiler by its own pressure and is carried by piping to whatever devices are to be employed for heating or processing. The pressure changes within the system provide transportation for the steam and also affects its physical properties. It is helpful to think of the typical steam system as a loop with 4 distinct sections. The first is generation. During this stage, in the boiler, heat is applied to water to raise its temperature. After the water has vaporized, the resulting steam moves into the second stage of the steam loop, distribution. This is simply the movement of the steam within a closed system to its point of use. The use, whatever that happens to be, is called heat transfer. This is the third stage. In the heat transfer portion of the steam loop, the heat of the steam is put to work doing countless jobs. As the steam gives up its heat through heat transfer or use, it condenses or changes its state, this time from a gas back into a liquid. This is called condensate. We'll learn later why it's very important to drain condensate from a steam system as quickly as possible. This is the job of a simple device called a steam trap. The fourth and final section of the steam loop is condensate return. Since condensate has already been through the steam system, it will take far less heat and fuel to turn it back into steam than it would to make steam of an equal quantity of cold water. That's why a growing number of steam users return the condensate back to the boiler where the whole process starts over, hence the concept of the steam loop. A discussion of temperature and heat is essential to an explanation of how water becomes steam. Click play to continue. Temperature is a measurement of the molecular motion within a substance. Water in a teapot, for example. Faster-moving molecules result in higher temperature. We measure temperature on a thermometer which sets the freezing point of water at 32 degrees Fahrenheit, and boiling point of water at 212 degrees Fahrenheit at sea level. Heat is a measurement of the movement or transfer of energy from a body with a higher temperature to a body with a lower temperature. We measure heat in British thermal units, BTU or kilojoule. 1 BTU is the amount of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. In SI units, the kilojoule is equal to a kilowatt second. Water can absorb only so much heat. This is called sensible heat because it produces a temperature change that can be measured. The amount of sensible heat that is required to raise the temperature of water from freezing to boiling is called the heat of the saturated liquid. At sea level, atmospheric pressure is about 180 BTU per pound of water. Adding more heat to water has no effect on temperature. Instead, it causes the water to change state, or vaporize, from a liquid to a gas. About 970 BTU of additional heat is required to vaporize 1 pound of water into 1 pound of steam. This is called latent heat because it cannot be measured by a thermometer. Water is made up of hydrogen and oxygen atoms. At lower temperatures, these molecules are loosely bonded to each other. When heat is transferred to the water, the molecules begin to vibrate and the temperature starts to rise. As the heat increases, the molecules vibrate more and more until the bond holding them together is severely weakened. When sufficient heat has been transferred to the water to break the bonds, the molecules explode apart, creating steam. After the steam has been transported to the heat exchanger, it gives up its latent heat to raise the temperature of some product or to power some operation. As the steam gives up its latent heat to the work effort, it condenses back into water. Click play to continue. Heat transfer takes place in 3 ways: conduction, convection, and radiation. Let's take a closer look. Click play to continue. Conduction is the form of heat transfer that takes place within a solid. Conduction causes the handle of a cast iron frying pan to be nearly as hot as the bottom. Conduction occurs within a solid or between 2 solids in contact with each other. It is generally believed that conduction occurs on the atomic level, much as the conduction of electricity takes place. Free electrons transport thermal energy from molecule to molecule away from the heat source. Click play to continue. Convection is the form of heat transfer that takes place within gases or liquids or between solids and liquids or gases. Convection causes the air from your heating system to be distributed throughout the room. Convection also requires physical contact. It takes place because of the difference in density in fluids as they are heated and cooled. Liquids or gases are heated and become less dense and rise. As they cool, they become denser and fall. In a system, this cycle of movement is called a convection current. Click play to continue. Radiation is the form of heat transfer that takes place between 2 bodies that aren't in physical contact. Radiation causes sunburns that many of us get when we've stayed out in the sun for too long. Radiation is the only form of heat transfer that requires no physical contact. While we do know that it occurs because of electromagnetic radiation, usually in the infrared band, much of our understanding of it is still theoretical. We do know that it can take place between 2 bodies separated by a vacuum and is partially explained by wave theory and quantum mechanics. Click play to continue. Often, heat transfer occurs as a combination of the methods we've discussed. For example, fire heats a frying pan by convection. The heat is then transferred from one side of the frying pan to the other by conduction. The egg in the pan is cooked by conduction heating. Click play to continue. Steam is complex. When we break down its properties and begin to understand them, we become closer to using the power of steam wisely. Click play to continue. In thermodynamic analysis, pressure is expressed in pounds per square inch above a perfect vacuum. This is called absolute pressure and is abbreviated PSIA. Steam pressure is usually measured in gauge pressure. The units are pounds per square inch gauge, or PSIG. It is a measure of pressure above atmosphere, at sea level. Below atmospheric pressure, steam is measured in inches of mercury vacuum. As steam pressure increases, so does the temperature, but by smaller and smaller increments as the pressure rises. There is a corresponding temperature for saturated steam for any given pressure. It is this fixed relationship between pressure and temperature that allows for precise temperature control in steam systems. Rising pressure in the system has an inhibiting effect on molecular movement. When water is subjected to higher pressures, more heat energy must be applied, and therefore higher temperatures must be reached before it can undergo the process of vaporization. As steam pressure increases, so does the heat of the saturated liquid. The amount of heat required to raise the temperature of a pound of water from 32 degrees Fahrenheit to the boiling point at a given pressure and temperature. It is expressed in BTU, British Thermal Unit, or kJ/kg. This occurs for the same reasons that the steam temperature rises with pressure. Again, the heat of the saturated liquid increases as the steam pressure increases. As steam pressure increases, the latent heat of the steam decreases. The amount of decrease diminishes as the pressure rises. Since it is the latent heat available for heat transfer that provides steam's greatest utility for non-temperature dependent processes, it should be apparent that lower pressure systems are most suitable for those applications. The decrease in latent heat occurs because there is a physical limit to the amount of heat that water can absorb in any state. As the amount of heat that is used to raise the water temperature before vaporization can take place increases, the amount of latent heat used to accomplish that vaporization must decrease. At approximately 3,206 psia, the amount of latent heat in the steam drops to 0 BTU per pound. 3,206 psia is the critical pressure for water. At that pressure, it absorbs the maximum amount of heat while in the water state and requires no more heat to turn it into a gas. At this pressure, water can exist either as a liquid or a gas at the same temperature. Add the figures for the heat of the saturated liquid and the latent heat together, and the sum is the total heat of the steam. The total heat of the steam increases with the system pressure up to approximately 435 psig. Therefore, the total heat decreases with increasing pressure. As the steam system approaches the critical pressure, little expansion can take place. The amount of latent heat added to vaporize the water begins to decrease rapidly to increase in sensible heat needed to bring the water to boiling temperature. This results in a decrease in the amount of total heat in the system as the pressure approaches critical for water. The amount of heat available from any medium in its current state is referred to as enthalpy. From steam, the enthalpy of the vapor is the same as the total heat of the steam. This is the sum of the enthalpy of the liquid, heat of the saturated liquid, and the enthalpy of vaporization. Differences in density are generally referred to by the measurement of specific volume. The unit of measure for a specific volume in cubic feet per pound, cubic meters per kilogram. As pressure increases in the system, the specific volume of the liquid rises marginally. Water is incompressible and therefore is not affected by steam pressure. As pressure increases, however, so does the steam temperature. This temperature increase results in greater motion in the molecules of the water and a slight increase in its specific volume. The specific volume of steam decreases as the system pressure increases. At atmospheric pressure, a pound of steam occupies about 1,600 times the volume of a pound of condensate. As pressure increases in the system, the specific volume of the steam decreases. Because of this principle, a greater quantity of steam is available in a smaller space, pipe, heat exchanger, at higher pressures. This is why steam is often distributed at higher pressure but is reduced to a lower pressure to perform specific heat transfer functions. Rising pressure constrains the molecules from moving apart when water vaporizes. At the critical pressure of 3,206.2 psia, the specific volumes of liquid and gas are equal. All of the properties of steam we have reviewed are interrelated. From any one known value, you can determine any of the others. These relationships are all displayed on a table called the Properties of Saturated Steam, or simply the steam tables. For a given pressure, you can read the steam temperature, the heat of the saturated liquid, the latent heat of the steam, the total heat of the steam, the specific volume of the saturated liquid, and the specific volume of saturated steam. The following measurements are expressed in imperial values. If you know that you need a temperature of 307 degrees Fahrenheit, the table tells you that you need to pressurize the system to 60 psig. If you have a 15 psi steam supply, the tables tell you that you have 945 BTU per pound of heat energy available to do work. Click the Links tab for the SI version of the steam tables. Click Play to continue. In this course, we learned steam and identified what steam is, learned how the energy of steam is used, and identified the many properties of steam.